Good afternoon, ma'am.
Yeah, good afternoon. So we'll start today. So welcome everyone to the course Nature and Properties of Materials. In week 3, we'll talk about metals and ceramics. So this course is offered by Professor Vishak Bhattacharya from Department of Mechanical Engineering, IIT Kanpur. I'm your TA, Alka Jange from IIT Kanpur. So firstly, we'll go through some sample assignment questions which will help you in solving your weekly assignments. And after that, we'll go through some lecture notes. Okay, so first question is, if you know the answer, then you can unmute yourself and tell what you think is the correct answer. So first answer is, which form is degradation form in polymers? Your options are swelling, dissolution, corrosion, and damping. So which one should be the correct answer here? Okay, so swelling would be the correct answer. Okay, in case of polymers, what happens if there are some solvents, they might uh, penetrate inside the polymer and it might cause some swelling in polymers. So this is one of the biggest degradation forms in polymers. And corrosion mainly occurs in case of metals. So because of the humid environment and reaction with water along with air. And damping is a phenomena of uh, that occurs in metals as well. So regarding this, we already studied in previous chapter. So corrosion is the prevalent in metals while swelling is seen in polymers. And the swelling is the penetration of a solvent into the polymer network, which can cause an abrupt change in volume. So volume increases for polymers because of this swelling. Okay, so next question is, iron carbon alloy containing less than 0.83% carbon is called. Your options are high speed steel, hypoeutectoid steel, hypereutectoid steel, and cast iron. So in this particular chapter, we'll learn about these categorization of steels and cast irons. So yeah,
Ma'am, it is in between hypoeutectide or hypereutectide because
okay, so for up to 0.8%, your material will be at 0.8%, it will be eutectoid steel. Above that, it will be hyper. Okay, and below that, it will be hypoeutectoid. So correct answer here, here because it's less, then it's hypoeutectoid. Okay, so hypo will be in this region. So here also you can see. Okay, so so the this amount will be in different books. It's between zero point 0.7 to 8, 0.76, or sometimes it's also written as 0.8%. Okay, so below 0.8%, you'll be having hypoeutectoid steel. Hyper meaning you understand that it will be higher. So hypereutectoid when there is carbon percentage is higher than this and lesser than 2.14%, because after 2.14% there will be eutectic reaction also occurring in your material. So when eutectic reaction starts, then your material will be known as cast iron. So below 4.3% carbon, your material will be hypoeutectic cast iron, and above that hypereutectic cast iron. And in case of steel, you will be having the division at the 0.76 or 0.83%. Okay, so this will be hypoeutectic steel. So here explanation is given here. So 0.8% is a eutectoid composition. So if carbon weight percent is lower than this, someone else has joined. Okay. So if carbon weight percent is lower than this, then it is hypoeutectoid steel. and if it is higher than 0.8%, then it will be called hypereutectoid, and exact 0.8%, then it will be eutectoid steel. And based on these percentages as well, your material structure, microstructure will also change. So after 0.8%, you will be starting to have cementite network along the grain boundaries, and below that you will be having some pro-eutectoid ferrite in material along with perlite. So perlite will be in both cases, in hypoeutectoid and hypereutectoid, but the pro-eutectoid phase will be uh, ferrite in case of hypo, and it will be cementite network in case of hypereutectoid steels. Next is, which of the following is an example of a mechanical metamaterial? So your options are rubber, glass, steel, or origami structures. So out of these, yeah,
Ma'am, I don't know about the metamaterial because I
okay, so
metamaterial.
I think sir will cover this in smart materials. So metamaterials will be uh, regarding the origami structures. Okay, so mechanical
Okay.
metamaterials are rationally designed structures of precision geometrical arrangements leading to unusual physical and mechanical properties. Here examples will be origami structures. Next question is, ladeburite microstructure in eutectic steel consists of alternating layers of two phases, namely gamma austenite and what is the other phase? So ladeburite is combination of, so in previous, here you saw, so eutectic reaction will be occurring at 4.3%. So after this you will be having your cementite, layers of cementite and ferrite in this case. So correct answer here will be cementite and austenite at the above stages. Okay, so ladeburite is a paste mixture of gamma austenite, FCC structure and cementite, and these phases exist in the form of alternating layers. So which type of mechanical metamaterials are capable of morphing into different shapes when subjected to external stimuli? So the previous question was also related to mechanical metamaterials. So the correct answer here again will be, yeah,
Origami inspired metamaterial.
metamaterials. Yeah. Others don't fall in this category. So programmable metamaterials, magnetic and self-healing, these all are part of smart materials, but not mechanical metamaterials. So here,
Ma'am,
yeah,
I have a doubt. Can I ask now or after completion of
yeah, yeah.
your?
You can ask now.
Ma'am, this metamaterial are really means work now. It is in workable condition. Means
Yeah,
is
yeah, yeah.
used anywhere.
Once let me check. So these are human-made materials with properties that are not found in natural materials. So we are just trying to, like these 3D type of structure that I showed earlier, right?
Yes, ma'am.
So
I got it. What is
yeah,
the concept behind it? But this the 3D structure. It is the lattice structure arrangement or multi-lattice structure arrangement. Means mm, I got you got my point, ma'am. I mean, I need
yeah, yeah.
means
It's like at atomic level as well, and at it can be at other level as well.
is there any example? Is there, ma'am? After complete of your work, can you means give me an example really which is after laboratory or is there any existence or real practical work of this metamaterial in the real world?
Okay, once let me check. So visual metamaterials. These are basically the structures that are like hollow structures and all that are made. So they are used for getting like light structures basically. So they are also used in some of the assemblies for reducing the weight of the entire system. So hollow materials that are made, they are used as these structures, origami type of structures, which are interwoven into like thin wires can be interconnected, or some other type of pillars, or these are interconnecting. So these are also used.
Clear.
Yeah. Okay, so researchers have developed a special class of origami metamaterials which show a constant value of Poisson's ratio when subjected to stress, and when a material is crushed or stretched along a particular direction, it undergoes a modification in the perpendicular or lateral direction. So the ratio between the deformation along the force and the deformation in a direction lateral to the force is called the Poisson's ratio, and the Poisson's ratio can be positive or negative. And in order to be useful, materials need to maintain a constant Poisson's ratio when they crumble under pressure. However, they are prone not to do so, and the Poisson's ratio varies as they deform. Next is, which of the following is the example of a mechanical metamaterial with a negative Poisson's ratio? So out of these options are carbon fiber composites, aluminum alloys, auxetic foam, or steel beams. So
Maybe
yeah,
third number, ma'am, I
yeah,
guess.
yeah, auxetic type of forms will be these are the structures of materials that have a negative Poisson's ratio, and when stressed they become thicker perpendicular to the applied force, and this occurs due to their particular internal structure and the way this deforms when the sample is uniaxially loaded. And the auxetics can be single molecules, crystals, or a particular structure of macroscopic matter. So as you asked earlier, right, so is it on like atomic level or other level? So it can be at single molecules level as well, and at macroscopic level as well. So as here it's shown as well. So these are the normal metamaterials, and in case of auxetic metamaterials, as you are applying stress in different directions, it will still give you negative Poisson's ratio. Next is any misinformation in the following rapid facts on steel alloys. So your options are chromium improves oxidation and corrosion resistance. So this one is correct, as you add the chromium in your iron. So what it does, it forms a chromium oxide layer. So this type of layer is impulsive in nature. So as we'll talk about pilling Bedworth ratio, then you will understand that chromium forms the chromium oxide, then this particular layer, it doesn't flake off, and it remains adhered to the steel. Okay, so this will provide good oxidation and corrosion resistance to the steel. Other is, that's why chromium is also added in stainless steels along with nickel. Next is sulfur decreases brittleness. So when sulfur is added in steel, it basically increases brittleness. So this is a wrong statement. Other one is nickel increases hardness. So nickel also increases hardness, that is a correct statement. So any type of impurities or any type of alloying elements that you add, it will provide some type of substitutional solid solution or interstitial type of solid solution. So these both type of solid solution strengthening will be there. So this will increase the hardness as well. Next is cobalt improves strength at high temperature. So as you have cobalt, this will also improve strength and at high temperature. So for hot hardness as well, at higher temperatures cobalt is used. Okay, so correct answer will be sulfur decreases brittleness, because it is a incorrect statement. So other statements are correct except sulfur decreases brittleness, because when sulfur impurity increases in an amount higher than 0.05%, it causes brittleness. And sulfur also forms sulfide inclusions which sit at grain boundaries, making steel brittle. So here also you can see as the this for various materials. So in case of mild steel, it shows ductile to brittle transition type of nature. So while in case of nylon and zinc, this transition is not that much sharp. So after minus 50 degrees Celsius, below this part, it has very low toughness, and above this it shows good toughness. So this type of phenomena is also because of sulfur. So as you might also know that the Titanic failure was one of the reason for Titanic failure was the presence of impurities such as sulfur and phosphorus in steel. So these impurities, they make ductile to brittle transition temperature much more higher. So at the when this Titanic it hit the glacier, so the temperature was very low. So there was a catastrophic failure of the ship. Next question is, carbon steel has blank weight percent of carbon. So the in case of carbon steels, what in case of steel, as I already told, what should be the percentage of carbon. So in case of cast irons, you'll be having carbon percentage higher than 2.1%, because eutectic reaction will start to take place. And 6.7 weight percent is the percentage that is in case of cementite, and 4 weight percent is again it will be in case of cast iron. So only correct answer will be the less than
Less than.
0.21%. Yeah,
Yes, ma'am.
again. Okay, so carbon steel is a steel with carbon content from about 0.05 up to 2.1% by weight, and it is up to which point the eutectoid product is made in steel on cooling. If carbon weight percent is more than 2.1 weight percent, then it falls in the cast iron category, as the eutectic reaction occurs which is characteristic of cast iron. Next is, which cast iron has graphite in flake form? So your options are white cast iron, grey cast iron, yeah,
Ma'am, a grey cast iron, ma'am.
yeah, grey cast iron, and in malleable and nodular. So what type of forms will be in other ones? Can you guess?
Nodular, that is the ring, means circular spherical type.
Spherical, yeah.
Yeah. And malleable cast iron, I don't know, ma'am. White cast iron, white flex, I think so.
In white cast iron, it will be in cementite type of layers. So
Yes,
when
ma'am.
you will be breaking it, so it will give you whitish type of uh, the failure fracture. In case of grey cast iron, you will be having the carbon in form of graphite, while in white cast iron you will be having cementite. In malleable cast iron, you will be having carbon in rosette forms, and in nodular it will be in spherical forms. Okay, here you can see. So in malleable iron, you'll be having this irregular type of shapes, and in ductile iron also you'll be having somewhat irregular and spherical type of shape. Nodular, spherical, then chilled cast iron, white cast iron, and grey cast iron. So in case of white cast iron, carbon is in cementite network form. In grey cast iron, graphite is in flake form. In malleable cast iron, graphite is in a irregularly shaped aggregate form. And in nodular, ductile cast iron, graphite exists in a spherical form. Next question is, an alloy has yield strength of 145 MPa. It has an average grain size of 2 micrometer. The Hall constant depicting resistance to dislocation is 80 MPa. If the grain size is reduced to 100 nanometer, what will be the new yield strength based on Hall Page relation? So your options are 226, 415, 105 MPa or 358 MPa. So for this you need to use the Hall Page relation. So Hall Page relation is given as sigma naught plus k upon under root d. So d will be your average grain size, k will be your coefficient. Okay, so Hall Page relation will be given as this: ky upon under root d. So your Hall Page relation showing the dependence of yield strength on average grain diameter can be given as this formula, where sigma naught and ky are the constants. So these two constants you need to find out from the first relation that is already given. So your yield strength is already given, your grain size is given, and the Hall constant is already given. So 80, this sigma I is given, so this is 80 MPa, and ky you have to find out, or you can directly put this value in the next equation and you can find out the correct answer for the yield strength for the reduced grain size will be 415 MPa. So this also you can check in a manner like, if your grain size is reducing, then your strength should increase. So after solving the question in exam, you can once cross check that it should increase, your strength should increase from the initial value.
Ma'am,
Yeah, yeah.
the constant value, whatever the ky you taken, so it is vary from material to material, or it is the 75 you taken here?
Ky you are solving from initial values. You are given yield strength and grain size and this Hall Page constant, right? So using those you will be finding out ky value. This will be constant for a material, sigma naught and ky. Okay, so these two constants are there. One of the constant is given, one constant you need to find out by initial values. Then you need to find out for the other grain size. Okay, so this value you
Clear.
have to put. Okay.
Yes, ma'am.
Okay, so next question is, what is the type of steel with 1.1 weight percent carbon? So out of these options, so as I told earlier, if it's more than 0.8%, it will be eutectoid, and steel won't be eutectic type of. So this can either be eutectoid, and out of those, if it's more than 0.8%, then it will be hypereutectoid. Next question is, which one is the result of increasing carbon in steel? So if you are increasing carbon in steel, what should happen? You should remember it in a way that if you are increasing the carbon percentage, which properties improve and which one decrease?
Hardness will increase.
Okay, so hardness,
Hardness.
along with hardness, your materials hardenability also increases.
Yes.
Okay, so hardenability meaning if your material has higher percentage of carbon, it can easily convert into martensite. Okay, when you will be quenching this material, it can easily convert into martensite. So when you increase the carbon percentage, its hardenability also improve. But weldability, so if your material has higher percentage of carbon, then welding becomes very tricky, because if you're welding your material, then in adjacent regions your material will turn into martensite. So because of that, there will be a lot of distortion in material and a lot of heat affected zone. So this will lead to the variation in properties in your material along with the your weld, where you have welded your material, and increase ductility. So ductility will also go down as hardness is improving and strength is increasing. That's why ductility will go down. So this is also not correct answer. And machinability. So as you keep on increasing the carbon percentage, so its machinability will decrease. because your material was softer earlier and ferrite was higher percentage. So as cementite will keep on increasing, its machinability will go down. Next question is, which metal is used as sacrificial anode? So for using sacrificial anode, your material should be highly reactive compared to the other material that you are trying to save from the corrosion. So if you have connected, for example, you are putting some coating or some material is connected electrically with the electrical connection to the material that you are using, then other material will more likely to get corroded compared to your material that you are trying to save. Okay, so this material should be highly reactive. So out of these materials, gold, silver and copper, all these are very highly noble in nature. So these materials are not likely to get corroded. So zinc will be the one of the materials that you can use as sacrificial anode. Next is, which one of the strengthening mechanisms is the result of dislocation multiplication? So out of these uh, various type of strengthening mechanisms, we'll study about this later, but in case of strain hardening or it's also called work hardening as well, strain hardening or dislocation strengthening. So in this case, what happens, you'll be deforming your material, and because of that deformation there will be dislocation loops generating in your material, and dislocation density will increase a lot. So because of this dislocation density increase, what happens, your material becomes uh, it becomes stronger compared to initial stage. So this will be correct answer here will be strain hardening. In case of composite strengthening, you will be adding some composite, meaning reinforcements in your material, and it will be providing strain to the material. In case of grain refining, you'll be reducing the grain size of material, and that's why these grain boundaries will prevent dislocation moment and will provide strengthening to material. In case of solid solution strengthening, you'll be adding some other element to this material, and this particular material will introduce some strain fields in material which will interact with the dislocations that will be moving, so that will also increase strength of material. Fifth question is, which metal oxide provides good adhesion to metal following pilling bedworth ratio, preventing corrosion? So your options are MgO, Fe2O3, Na2O or NiO. So out of these, this magnesium, sodium oxide and iron oxide, all these materials have pilling bedworth ratio either uh, in categories where these layers won't be stable. So only for nickel oxide and chromium oxide, these some of the materials it will be stable, this layer. So only for nickel oxide, this pilling bedworth ratio will be of correct order. So I think there is. Okay, so now we'll go through lecture notes. So firstly, classification of materials. So in case of metals and ceramics, we'll talk about in this lecture. So metals can be classified into ferrous and non-ferrous type of metals. In case of ferrous, you have materials which are mainly based on iron, ferrum, which is iron. Okay, so ferrous can be classified into two main categories, steel and cast iron. Steel are the ones with the carbon weight percent less than 2.1 weight percent, and in cast iron you will be having carbon weight percent more than 2.1 weight percent. And in case of non-ferrous materials, you will be having all elements, all metals which are other than iron. So aluminum, titanium, copper, bronze, all these metals and alloys, they will be non-ferrous. Firstly, you have iron. So the Iron Age, it began between 3000 years ago and it continues today, because most of our materials are even today it consists of steel. So most of the materials you'll be seeing around you, it's either made of cast iron or steels mostly. And the carbon forms an interstitial solid solution when it's added to iron to form steel, as the atomic radius of the carbon is 0.071 nanometer atom, is much less than that of iron atom size, which is 0.124 nanometer in size. Use of iron and steel has changed drastically the human development. Now, iron possesses allotropy, which means it exists in two or more different forms in the same physical state. So, when it's in solid state, it still has different forms, different crystal structures. So, it can be in BCC and FCC structure. So, from temperature less than 770 degrees Celsius, it will be in alpha form. So, this is ferrite, alpha iron. It will be ferromagnetic in nature. Okay, so it will attract magnets and it will be having crystal structure which is BCC. So, body centered cubic type of crystal structure. And if your temperature is between 770 to 912 degrees Celsius, then it will be beta iron. So, this transition will be at this particular temperature 770 degrees Celsius. So, this is also known as Curie temperature. So, here your material will change from ferromagnetic to paramagnetic. So, your steel, your iron will no longer attract magnets and your material will be still BCC crystal structure, but it won't be ferromagnetic. And from 912 to 1394 degrees Celsius, your material will show FCC type of crystal structure. So here it's known as austenite or gamma iron. Next is after 1394 to 1538 degrees Celsius, your material will again be in BCC crystal form and known as delta iron. So this BCC structure and this BCC structure are different because the lattice parameter size is different. The A here will be different for these two, and other than that the crystal structure will remain same, and after this temperature it will melt. Then the classification of steel. Yeah, you can ask.
Ma'am, the previous slide, yes, ma'am. So in this slide, the BCC structure and the this BCC structure, what is the difference? You tell me.
The lattice parameter. So in previous slide, previous lecture I told, right, in BCC structure you have the lattice parameter ABC, right?
Yes,
three
ma'am.
three different direction in x, y and z axis. So in case of cubic, all these A will be equal and it is A, your lattice parameter. So this parameter will be different for the ferrite one and it will be different for alpha and delta iron.
Okay, ma'am.
Okay,
Ma'am,
then,
another thing.
yeah.
Ma'am, another thing that this is at the high temperature, 770 to 1530 degrees Celsius. So in between that, the researcher how they recognize that the structure is changed, because if it is cooled down, automatically the structure will change. But at the molten state, how they ma'am tell that it is in FCC crystal or either in alpha, gamma, whatever that.
No, after melting there won't be any type of crystal structure. After 1538 degrees Celsius, it will be in liquid form. So liquid form, there is no long range order.
No, ma'am. Here it is 912 degree to 1394. That is
Yeah,
in FCC
this one.
structure. Then how they measure it? Because this is also in the hot condition in the laboratory. How they handle all these things?
Okay, so it particular this temperature. So FCC type of crystal structure they can. Uh, so basically these crystal structure you can find out using XRD, right? So XRD can be done at higher temperatures as well. it's not that tricky,
Okay,
but yeah, it can be done for higher temperatures as well. And also, like, this particular temperature is for the pure pure steel, right? So if you add some other elements as well, so this particular temperature, it comes to room temperature. Even if you add a lot of nickel to this steel, this iron, then this gamma type of structure, it will be stable at even room temperature. Okay, so this way you can get FCC structure at room temperature also.
okay, ma'am, clear.
Okay. Next is the classification of steel. So steel is firstly classified into two types: low alloy steel and high alloy steel. So alloying element will be lesser than say 10% in this case, and higher than that it will be high alloy steel. So in case of low alloy steel, you have again classification into low carbon steel, medium carbon steel and high carbon steel. So the carbon weight percent, if it's less than 0.25 weight percent carbon, then it will be low carbon steel. 0.25 to 0.6 weight percent, then it's medium carbon steel, and then above that, zero point 0.6 to 1.4 weight percent, it will be high carbon steel. Then in case of high alloy steel, you have tool steels and also stainless steels. In case of stainless steel, you have around 11 to 12% chromium in it, and 6 to 7% nickel also in it. So firstly, we have low carbon steel. So it contains less than about 0.258% carbon with mild steel, and it's relatively soft and weak, and it has outstanding ductility. So because it has very low carbon weight percent, so it doesn't have that much strength, so it will be ductile, so it can be easily made into sheets and thin wires. So it is used for various structural application where that much strength is not required. So it provides 25% of elongation, and it has good toughness as well, and also it has high machinability and weldability, and it is least expensive to produce. Okay, so it doesn't require the equipments or tools which require uh, that much of strain, because the strength of material is lesser here. And then the tensile strength here is between 415 to 550 MPa. The application of this steel is in making beams, channels, nuts, bolts, wires and tin cans, etc. Then in case of low alloy steel, it means it contains alloys such as copper, vanadium, nickel, molybdenum up to 10 weight percent, and if more than 10 weight percent, then it will be high alloy steel. Okay, so in this case you have high strength and corrosion resistance compared to plain low carbon steel. In case of plain low carbon steel, you don't have any of these alloying elements to higher weight percentages. Okay, so these elements, they provide this nickel, chromium and copper. These three main elements, they provide good corrosion resistance. Next is tensile strength for these is up to 700 MPa. So you can compare here from 400 to 700 MPa. This much increase will be due to substitutional type of this substitutional solid solution strengthening. Next is medium carbon steel. So this one consists of 0.25 to 0.6 weight percent carbon, and it is stronger compared to low carbon steels, but of low ductility and toughness. Okay, so these so ductility is reducing because of the higher carbon percent. So it has higher strength but reduced ductility and toughness, and it has good wear resistance. That's why it will be used in case of gears. And plain carbon steel, its tensile strength up to 850 MPa, and in case of alloy steel, this medium carbon steel, it will be having tensile strength up to 900 MPa, so almost twice. And applications will be in case of railway steel, railway wheels and tracks, gears, crankshafts, etc. So all these require high strength. Then we have high carbon steels. So these will be basically used in tools because of high carbon percentage. So these materials will be having very high strength. Yeah, am I audible now?
Yes, ma'am, but voice is not clear.
Okay. Uh,
Now okay.
okay. Okay, I'll keep the mic near. Okay, so in case of medium carbon steel, you have carbon weight percent from 0.25 to 0.6 weight percent carbon. And it is stronger compared to low carbon steels, but of low ductility and toughness. So I already told, I'm repeating because of voice break. So here you'll be having ductility and toughness reduced because of high percentage of carbon. So as the carbon is keep on increasing, it will go in interstitial and it will make your iron more stronger. But on the expense of ductility and toughness, these two will reduce. So these are always inversely proportional. So if you keep on increasing your material strength, then ductility is more likely to reduce. And then it also has good wear resistance, that's why it's used in making these gears, crankshafts. And in case of plain carbon steel, it will be having tensile strength of up to 850 MPa, and in case of alloy steel it will be having almost twice 1900 MPa. In case of high carbon steel, you have carbon up to 0.6 to 1.4 weight percent carbon. So these type of steels, these will be very brittle in nature. So these materials won't be used in structural application, but they will be mostly used in making tools and dies, which require high strength only, not much toughness. And these can be alloyed with carbon and other metals to form very hard and wear resistant materials. So when you add some alloying elements for making tool steels, what you do, you add a lot of these type of metals, and these metals will form carbides. So these carbides, they provide very higher wear resistance. So applications include cutting tools, dies, saw, and concrete drills, etc. Next is tool steel. So this is type of alloy steel, right? So stainless steel and tool steel, these both will be having alloying elements more than 10 weight percent. So it is commonly used in drill bits and other rotating cutting tools. And it can withstand high temperatures without losing its hardness and toughness. Examples include, so in this case you have 1841, and you also, in case of 188 steel, that is type of stainless steels. And here 1841, here you have 18% tungsten, 4% chromium, and 1% vanadium. So this question is also asked various times. So this percentage you should remember: 18% tungsten, 4% chromium, and 1% vanadium, with a carbon content of 0.6 to 0.7%. So for formation of carbides as well, you require this much of carbon. Cobalt high speed steel, it provides material heat resistance, so it's increase heat resistance. So you can use these materials to very high speeds as well. So because of the friction, a lot of heat will be generated, but the cobalt will take care of this particular problem. Next is molybdenum high speed steel. Molybdenum increases hardness and wear resistance, and also the it is cost effective replacement for tungsten in tool steels. Okay, so instead of tungsten you can add molybdenum as well, and it is cheaper compared to tungsten. Next is stainless steel. So example in,
Ma'am,
yeah,
ma'am, I have a question.
yeah, ask.
Ma'am, the whatever the we add the in means the molybdenum or whatever we add, So
Yeah.
that is due to this interstitial defect only. It is caused this high strength geometric pattern, or anything else also.
No, see, molybdenum size is higher compared to even iron, or it will be equivalent to those. So it, in this case, it won't be interstitial. Interstitial will only be nitrogen and carbon. And after most of those elements, they will go as substitutional elements. So it will
So
come instead of carbon. So substitutional type of solid solution will be there, and also carbide will form. So if you are forming, for example, some vanadium carbide or tungsten carbide, these type of elements, the carbides, they will be type of ceramic elements, right? So these type of elements are present there, so they will they will act as barrier for dislocation movement. So they will again provide you with the dispersion type of strengthening. So solid solution strengthening as well as dispersion strengthening.
okay, that means these elements are act as a substitutional defect, and they provide hindrance, or they give hindrance to the slip, plane
Yeah,
slip. Okay,
slip of your so how your material will deform, there should be dislocation movement. So that dislocation, if anything you are doing in your material that is providing a barrier to your to this dislocation movement, then it will be providing this strength to material, right?
yes, ma'am. So that means if we come to know that at what type of at which amount of the force, how much dislocation happen if we add some substitutional defect there, and how much it resist, then we go for the choice of either we go for the chromium or vanadium, like that we go.
Yeah, how much, yeah, and based on that, and also what type of property you require. So, for example, in case of tool steels, you prefer that that the elements that you are adding, they form carbides. So, vanadium and these tungsten, these form carbides. So, you choose these. But in case of stainless steel, you choose chromium and nickel. These two provide, these are more likely to form oxide layer at the top, so it will provide corrosion resistance. So stainless meaning it doesn't form any corrosive layer, so it provides corrosion resistance. So what is the end application? According to that you have to choose which material you will be adding.
Clear, ma'am. Ma'am, another question is that previously you tell that that 6% of carbon content is for the cast iron and all these things. The weight percentage, that means in 100 kilo of the steel we add 6 gram of 6 kilo of carbon by weight.
Yeah, by weight 6%.
So
6
that
point,
means
yeah, 6% is not there. 6.7% is for cementite. If you are taking cementite composition, in that case you'll be having 6.7% of carbon and another percent will be of iron. You, if you are choosing cast iron, then it is more likely between 2.1 to say 5% or something, less than 5%.
okay, that means in 100 kilo it is nearly 5 kilo.
Yeah.
So ma'am, so how they means how in actually how they add in the carbon form, it is in the coal form, means how they add in the furnace, or they how they confirm that okay this is purely, so if we make prepare a dish something, then we can check oh salt is added completely or not. But in this case it is in the molten metals, they how they confirm that this all the carbonates go thoroughly uniformly all over the furnace, then this is prepared whatever they.
Okay, so at the that temperature that you are melting your steel, so basically steel is mainly made using this recycling type of process. So you take scrap and you melt it, and then you'll be adding whatever the elements to reduce the oxygen percent. So here you'll already be having carbon percent. So you don't add carbon intentionally, but it will be already having. So in case of other type of processes as well, you use pig iron as the raw material for this steel forming. So in case of pig iron also you have a lot of carbon percentage, up to 4 weight percent of carbon already in it. Okay, so you'll be trying to dilute that carbon percent. You basically add oxygen to it so that CO2 forms, and this carbon is going outside of the steel. So you already have the carbon percent, you have to bring it to the that required percentage. You don't basically add carbon to it, but you can add as well if you have pure iron in that case.
Okay, ma'am.
Okay. Okay, so next is we have stainless steel. So it is very highly resistant to corrosion in a variety of environments. We covered tool steel. So it has predominant alloys, chromium, and to balance this chromium is basically uh, to balance this we also add nickel as well. So chromium will be up to 11 weight percent, and up to 6 to 8% you'll be adding nickel as well. And one of the example is 18 at stainless steel, in which you have 18% chromium and 8% nickel. The applications include in cryogenic vessels, in food processing equipment. So why in this case? Because if there is some rust or some this corrosion layer is formed, then it will react with your food and it might render your food poisonous. So that's why you need to use steels which are stainless in form, so it doesn't corrode with time. Another one is gas turbine parts, high temperature steam boilers also, they'll be in contact with water at high temperatures, so it should not corrode with time. Heat treating furnaces and nuclear power generating units, all these are some of the applications of stainless steels. Now these are some of the roles of various elements that you add into steel. So effect of alloying elements. So first is boron. So boron is basically added to improve hardenability. So if you add boron, then your material will easily transform into martensite. So it improves hardenability without loss of machinability. Chromium, it improves oxidation at high temperature, and it provides corrosion resistance. And also corrosion resistance may also be enhanced by nickel and molybdenum additions. So nickel and molybdenum also form oxide layers which are impervious in nature. Cobalt and tungsten, these both improve strength and hardness at elevated temperatures. Sulfur, it improves machinability when combined with manganese. So manganese sulfide which forms in steel, it provides some chip type of nature in steel. So if you're machining your material, it provides easy machining. And if there is no manganese present in your steel and you are adding it alone, then it increases brittleness and it lowers impact strength and ductility of material. So it can be having a bad impact in steel if it's added alone. Manganese, it improves hardenability. So instead of boron and nickel, you can replace it with manganese as well. In some of the steels, when you replace it with manganese, it doesn't provide very good corrosion resistance. So it's some of the steel you'll be purchasing, you'll be seeing that after some time it will be corroding. Okay, some of the steels that you use as vessels in your kitchen, then they're more likely to corrode in some few days. So those are the steels where they exchange nickel with the manganese. So though it will be stainless steel, but it won't be providing that much of oxidation resistance. Okay, and it also improves wear resistance, and it counteracts the brittleness that's caused by sulfur. So it interacts with sulfur and takes care of this sulfur, and it doesn't let it become brittle. Next is molybdenum. It improves hardenability and toughness of material, and it also improves elevated temperature strength and creep resistance. Nickel increases strength and hardness without sacrificing ductility. So compared to other these elements, if they are improving the strength, they will be deteriorating the ductility, but not with the nickel. And uh, it also doesn't sacrifice ductility and toughness. In case of vanadium, it increases strength, hardness, wear resistance, and resistance to shock impact at high temperatures. Next is titanium. It improves strength and deoxidizes steels.
Ma'am,
Yeah.
ma'am, nickel, in the nickel, it will the strength, hardness, sorry, strength also increases, but without sacrificing the ductility. When how it is possible, ma'am? Without, if strength is more, then it should be resist to deform. Means it can. Then how it is possible?
Okay, so in case of when you add nickel and iron are sitting very close in periodic table. Okay, so when you'll be adding nickel, it will be just replacing iron and won't be producing as much of lattice mismatch compared to other type of these elements that you're adding. Okay, molybdenum is very has very bigger atom compared to nickel, so that's why, like, if you're replacing it with nickel, then it won't be affecting ductility as much. It will be reducing ductility, but not as much as other elements. So this ductility and toughness, it is retained in case of when you're adding nickel, because nickel is FCC type of nature, so it doesn't it also has its own ductility as well.
Clear, ma'am.
Okay. Next is cast irons. So in case of cast iron, you will be having various types of cast iron. First you have gray cast iron, and this is the structure of gray cast iron, where you have these graphite flakes type of nature. So these flakes have these type of notches. So from this, there is more likely to this fracture start to initiate. So these act as concentration regions, stress concentration regions. So in this case, carbon content varies from 2.5 to 4.0 weight%. And this graphite exists in form of flakes. This graphite flakes, they give self-lubricating properties and vibration damping capability. And the strength and ductility, they are much higher under compressive loads. Okay, so and the tensile strength is between 120 to 280 megapascal. And the applications include base structures for machines and heavy equipments that are exposed to vibrations. So for the machines such as lathe that you use in your workshops, those are more likely to have base which will be made of cast iron, because these have very high damping capacity. So the vibrations are reduced a lot, and it will be uh, reducing the noise because of that particular damping. Okay, and graphite, as you know, it is also used as lubricant in some of the cases. So in case of cast iron that you are using, so this will be providing self lubricating properties, and this vibration damping capacity will be also because of this graphite. Next is white or chilled cast iron. So in this case, you have no graphite, and carbon will be in form of cementite, which is the hardest constituent of iron, and it is formed by rapidly cooling molten iron. So you have molten iron and you are rapidly cooling it. And here in this case, gray cast iron, so to form this graphite, you require slow cooling, or you need some type of heat treatments for the formation of graphite. While in case of chilled cast iron, because of the fast cooling, you will be getting cementite structure, and it is formed by rapidly cooling, and it is very hard, wear and corrosion resistant, and it is almost non machinable because of the presence of this cementite. It is non machinable, so the final shapes are already made into by cooling itself, by casting, so that there is no other machining required. So application includes rollers and rolling mills. And this is the microstructure here. So there will be perlite type of structure along with some cementite structure. Next is cast iron. So malleable cast iron. In this case, it is formed by heating white cast iron. So white cast iron we took from here, and we are just providing some heat treatment. So we are heating it between 800 to 900 degrees Celsius for a prolonged time in a neutral atmosphere. So there is neither reducing type of or oxidation type of atmosphere, but neutral to prevent oxidation, and it leads to the decomposition of cementite, forming graphite in the form of clusters. So your cementite will be Fe3C, right? So your iron will be going into matrix and your carbon will be forming this graphite, and this graphite will be in form of some clusters. And this malleable cast iron is highly shock resistant, and it is also has high toughness, and the tensile strength will be between 350 to 450 megapascal, and it can be hammered to a small thickness. Okay, and the applications in making connecting rods, transmission gears, pipe fittings, and valve parts. Next is nodular, ductile, or spheroidal cast iron. So it is obtained by adding small amount of magnesium or cerium, okay, from 0.1 to 0.8% to molten gray cast iron, and this leads to formation of graphite in the form of spheres. So these magnesium, it will act as nucleation sites for these graphite spheres, and these particular material also has high fluidity. So it will, when it will be solidifying, the shape will be very highly finished because of high fluidity. So if you have very complex dye that you are pouring your material in, so that particular shape will be easily taken because it has high fluidity. So okay, I think where is iron carbon diagram we had initially, right? So for eutectic type of structures for up to 0.4.3% of carbon, this particular part is coming from here, totally liquid, complete liquid to solid, right? So this region is the, should be, this will be, this gap should be the closest, smallest, then it is more likely to have high fluidity. So this fluidity is high, then it will be forming very complex shapes easily. So this eutectic type of structures are, that's why, used in making very highly finished castings. So this is also in case of some of the um, tin alloys as well. Lead tin alloys which were previously used but now they are not used. Okay, next is they have also good toughness and high wear resistance, and they also have high tensile strength up to 400 to 900 MPa. So it is almost twice the malleable cast iron, and it also has good machinability and good weldability. Okay, machinability was very poor in case of chilled cast iron. Next is effects of impurity on cast iron. Okay, so these impurities can be silicon, sulfur, manganese, and phosphorus. So in case of silicon, it provides formation of free graphite. Silicon is one of the graphitizers. So if there is silicon present, then your carbon is most likely to form graphite rather than cementite. It makes iron soft and easily machinable. So if your carbon is coming out as graphite, then your remaining material is more likely to be ferrite. So that's why this material will be highly soft and easily machinable, because if it's in form of cementite, then it will be almost non-machinable. Next is it produces sound casting free from blowholes as having a high affinity to oxygen. Okay, so if there is silicon present, then it will be attracting oxygen, so SiO2 will be forming, so there won't be any oxygen remaining in the casting, so there won't be any blowholes present in your casting. Next is sulfur. So it makes cast iron hard and brittle, and if it's above 0.1%, it makes unsound casting. So sulfur has negative impact on your cast iron. Next is manganese. So it makes cast iron hard by formation of carbide. So if there is presence of manganese, then carbides are more likely to form. It keeps control over harmful effects of sulfur. So in case of steel also, I told earlier that manganese and sulfur form manganese sulfide, and it's more likely, it the sulfur being in any other form such as iron sulfide, it's less harmful, manganese sulfide. Okay, so it keeps control over harmful effect of sulfur. And in case of phosphorus, it imparts fusibility and fluidity, but it induces brittleness. So if phosphorus is there, as I told earlier as well, in case of steel as well, if you have sulfur and phosphorus in your casting, then it's more likely to make your material more brittle. So it imparts fusibility and fluidity, but it induces brittleness. Next is non-ferrous type of alloys. So the classification is in case of heavy alloys and light alloys. So it's based on density. So if your density is very high, then these alloys will be called heavy alloys. And these include copper, nickel, cobalt, etc. in their alloys. And in case of light metals or light alloys, you have aluminum, zinc, titanium, etc. in their alloys. So as in automobile sector or aerospace sector, when you are trying to select materials for your for making aeroplanes or automobiles, you try to choose materials which are lighter, so the fuel consumption is lesser. So that's why aluminum and titanium are being researched a lot. Next is aluminum. So aluminum has a crystal structure of FCC, which is face centered cubic. So as I told in previous chapter as well, face centered type of structures have a lot of slip systems, which will render this material a lot of with having a lot of ductility and toughness. And its melting point is also very less, so it can be easily casted. So 660 degrees Celsius is very less compared to other metals. So this material is used in applications which use service temperature which are less, and density is, yeah.
Ma'am, which material have a more planar density than the slip direction also, the slip plane is that plane only, na?
Slip plane and slip system. So slip plane will be the particular plane and direction will be perpendicular to that particular plane.
Yes, ma'am. Means the on the
So
chosen
the
plane.
densest, yeah, densest place, so in which direction you will be having highest number of atoms, so that particular direction will be your slip direction, and the plane which has the highest amount of atoms, that will be your slip plane.
Okay, ma'am.
So combination of those will be the slip systems. So I think we'll talk about that in coming chapters as well, or I'll see. If not, I'll add slide in next chapter.
Ma'am, no, ma'am. I ask means if a given lattice structure, we can identify how many slip plane which associate with it, a given lattice structure.
Yeah, so if you have FCC type of structure, you have 24 slip systems, but it can change depending on metal as well. So for some FCC metals, you have different number of slip systems as well. Okay, so for HCP also you have depending on C over A ratio. So C is C direction, the above direction, and divided by A direction. So if this ratio is different for various metals, so that's why slip systems are different for some HCP systems as well. But for generalization, you can say that FCC type of structure has 24 slip systems, HCP type of system has 3 slip systems or something like that. Okay,
Okay, ma'am. So that means which lattice structure is more slip system? That means that is
ductile.
more ductile. Okay.
Yeah, it can be easily deformed because there are a lot of slip systems.
Okay.
So
If one is restricted, another is perform.
yeah, so if your dislocation is moving from one slip system to another, if there are a lot of options for it, then it's more likely to change the slip system and easily bypass the barrier. But if you have very less number of slip systems, then you're more likely to be restricted with those slip systems and your material will be very brittle in nature. So for BCC and HCP compared to FCC, they are much more brittle. FCC is the has the highest number of slip system. That's why it is the ductile type of system.
Clear, ma'am.
Okay. So its density is also 2700 kg per meter cube, which is very light. And then you have elastic modulus, which is 70 GPa, and it is silvery grayish luster metal, and it has very high thermal and electrical conductivity as well. So it is used in making these type of fins that you also use, that you might have seen on the radiators as well. So radiators will, what they'll basically do, so whatever the system that is running behind it, it will take heat from this and it will radiate this heat out to the environment. So because of high thermal conductivity, these copper and aluminum is basically used for making these radiators, and aluminum is very lighter compared to copper, so it is preferred. Next is titanium. It is also again one of a light metal, and in case of pure titanium, it has very low density for uh, 4500 kg per meter cube, and it has high melting point 1660 degree Celsius. So for applications which require low density as well as high temperature, high service temperatures, such as in case of these aerospace applications, we choose titanium over aluminum because aluminum has melting point only 660 degree Celsius. And elastic modulus is 107 GPa and tensile strength is 150 to 500 MPa. The appearance is similar to aluminum, silver, grey, white, metallic luster, and applications are in high strength and temperature components, biomedical jewelry, etc. In this case, alloying is required to reduce cost because this material is costly compared to other elements that we'll talk about, and it increases strength and also controls phases if we are alloying the titanium. There are basically two crystal forms that are present. Below 883 degrees Celsius, you have alpha structure, which is HCP, and beyond 883 degrees Celsius, you have beta structure, which is BCC in nature. And there are four alloys: alpha, near alpha, alpha beta, and beta type of alloys. And alpha phase stabilizers are aluminum, gallium, germanium, carbon, and nitrogen. And beta phase stabilizers include molybdenum, vanadium, tantalum, niobium, manganese, iron, chromium, cobalt, nickel, copper, and silicon. Next is zinc. It is crystal structure is HCP in nature. So zinc is less ductile compared to your FCC type of structures, and its melting point is 420 degrees Celsius, which is again very less. so it can be easily casted, and its density is 7140 kg per meter cube, and it has silver grey lustrous appearance, and it is easily castable, okay, because of the very low melting point. And its application include galvanic coating on steel. So one of the process known as hot dipping. So here your steel is dipped into molten zinc, so there will be an even coating of zinc. So this zinc coating, it will provide corrosion resistance to the steel. So what will happen if you have a coating of zinc, your zinc is more likely to form zinc oxide, and this layer will be remaining on steel as it is. Okay, so if you have zinc oxide layer, so your iron which is below this, it is more likely to remain uncorroded. Even if this layer breaks, so what happens, there will be formation of some anode cathode, so this layer of zinc on other spaces is more likely to get corroded rather than the steel itself. So it will provide steel from oxidation for a lot of time. And then you have corrosion protection of structures by attaching a sacrificial anode. Then you have zinc carbon dry battery, and zinc carbon dry batteries are some of the new application of zinc. And then also in dietary intake, so if you have deficiency of zinc, then it leads to weak immunity, slow brain growth, diarrhea or pneumonia, which is found, this zinc is found in spinach, cashew, seafood, cocoa and beans, and there are supplements of zinc also available. Next is copper. It has crystal structure of FCC, and its melting point is 1085 degrees Celsius, and its density is 8920 kg per meter cube, and it has distinctive reddish orange color, and its corrosion resistance is very high, okay, because it's one of it is, if you see the reactive series, then copper will be near gold and silver, so it is very noble material. So it will be, once forming the copper oxide on the layer, then it will be impersive layer, and it's more likely to remain uncorroded. And also it has good corrosion resistance, and it is soft in nature when it's in pure form. It's also malleable. Malleable meaning it can be made into thin sheets. Ductile, it can be made into thin wires, and it is very tough, and it also has good machinability. It also has high electrical and thermal conductivity, and the thermal conductivity order is, for silver it's highest, then for copper, then for aluminum. Okay, so as we know, silver is very expensive, so silver can't be used for the normal wires that we use in our day-to-day life. That's why we move to the either copper or aluminum. So we sacrifice for the conductivity, but we take the lower cost of the copper and aluminum. Then at the 99.99% pure copper, it is used for wiring applications, and it possesses around 97% conductivity of silver at 1/8 of the cost. So because of very less cost compared to this, we can sacrifice this much of conductivity. And these are some of the applications in making tubes, wires and these vessels. Next is nickel. So its crystal structure is again FCC, and its melting point is 1455 degrees Celsius, and its density is 8900 kg per meter cube, and it has silvery white luster, okay, similar to aluminum, with a slight golden color. And its applications include nickel metal hydride rechargeable batteries, in making monel metal, which is alloy of copper and nickel, and then also in primarily composed of nickel and copper with traces of iron, manganese, silicon and carbon, this monal metal. And it is also has strong corrosion resistance, and it is used in this monal metal is used in heat exchanger tubes, food processing plants and marine applications. Next is in making superalloys based on nickel and chromium. So these some of the superalloys, these are high creep and oxidation resistance at elevated temperatures, approximately 1100 degrees Celsius, and in making used in making turbine blades. Next is cobalt. This also looks lustrous silver gray metal similar to aluminum, and its crystal structure is SCP, so it is brittle compared to other metals, so it can be easily made into sheets. Its density is 8900 kg per meter cube, and melting point is 1495 degrees Celsius, very similar to nickel, and its elastic modulus is 205 GPa. The main application include production of high performance alloys, and cobalt based alloys are also corrosion and wear resistant. And some of the high speed steels, they also contain cobalt for increased heat and wear resistance. Also used in medical orthopedic implants, Betaluum, which is cobalt, chromium and molybdenum based alloy. Okay, as I told earlier as well, in high speed steels, cobalt is added for increasing heat resistance and wear resistance. So at higher temperatures also you can use these tool steel. And it is alloyed with 95% of platinum for jewelry making, and cobalt is based blue pigments impart a distinctive blue tint to the glass. So it's added to the glasses as well. Next is strengthening mechanism. So you have a lot of questions, I think, in exam and in assignment as well based on strengthening mechanisms. Okay, so it is the ability of material to plastically deform, depends on the ability of dislocations to move. So if you are deforming your material, you will be applying some force to your material, some load to your material, then the deformation, it requires formation of dislocation and the movement of these dislocations. Okay, so if you are restricting or hindering this dislocation motion, then it will make your material harder and stronger. So some of the mechanisms to strengthen metals are grain refining, solid solution strengthening, strain hardening, precipitation strengthening, martensitic strengthening and composite strengthening. So last two strengthening mechanism we won't talk in detail, so I'll briefly tell. So in martensitic strengthening, what happens if you have steel and you're quenching your steel? Quenching meaning you're cooling it from the austenitic region to very fast you're cooling, then it's more likely to transform into martensite. So your martensite has the highest strength in some of the after cementite, this phase of the steel has the highest strength. So if your steel is forming martensite, then this type of strengthening will be martensitic strengthening. And in composite strengthening, you can consist some reinforcements which you can add some for example, you can add some rods, whiskers, some precipitates or some small particles to your material matrix, then it will be having some strain to it and it will be composite strengthening. Now first is grain refining. So in this case you have a fine grained material which has small grains, is harder and stronger compared to coarse grained due to a greater total grain boundary area to restrict dislocation motion. Okay, and this Hall Page relation, it's given as sigma naught equals to sigma I plus ky upon under root d. So here sigma naught will be your yield strength of material. Sigma naught will be your friction stress which opposing to the motion of dislocation. So this is the material quality. Okay, and next is ky, which is the extent to which dislocations are piled up. So it depends on history of your material. So before you are applying this other force, before that how much plastic deformation your material already has undergone. So that will depend on this ky. Next is d, which is average grain size. This t is in under root d. Okay, so from this relation also you can see if you're increasing the size of grain, then your yield strength is more likely to go down. The critical grain size, which is typically around 10 nanometer, the yield strength would either remain constant or decrease with the decreasing grain size. This phenomena is known as inverse Hall-Page relation. So if you keep on decreasing your grain size even below 10 nanometer, then this rule will break, and then breakage of this rule is known as inverse Hall-Page relation, and above this it is Hall-Page relation. And this is how your grain boundary will look like. These are the areas of where there is no ordering, and if your dislocation is moving on this slip plane, and here if it's moving, it will be facing this grain boundary, which is a barrier for it. So from going from this slip system to this slip system, this will require extra force to it. Okay, so that's why this grain boundary will add some strain to your material. Next is solid solution strengthening. So in this case, the pure metals, they are almost very softer than their alloys.
Ma'am,
So yeah,
uh, if grain size is increases, that means the material is weak, na ma'am?
if grain size increases, yeah, if your material has a grain size which is bigger, then your grain boundary number will be less, right?
Yes,
So
ma'am.
the number of grain boundary, if you keep on increasing, your density is increasing of this grain boundary, then more the barrier will be in your material. Okay, so if you are making your grain size smaller and smaller, only up to 10 nanometer, below this rule will break. So above 10 nanometer, you are reducing the grain size, then the number of grain boundary is will be less and less if you keep on decreasing the grain size, and you'll be facing these more and more grain boundary for movement of these dislocation. So that's why strength will increase.
Okay, ma'am. And another thing, ma'am, how the grain boundary is formed?
How the grain boundaries will form? So I think, have you studied about casting like in some other courses?
Yes, ma'am. I know basically means, but the reason behind it is actually not clear.
Okay, so when you will be casting your material, what happens? There will be a lot of nuclei forming. Okay, so at the same time, a lot of nuclei are forming. So this nuclei will keep on growing. It can grow based on what time or what cooling rate you apply for your material. If you are applying cooling rate very fast, then what will happen? A lot of nuclei will be there. So these nuclei will get less time to grow. So less time will grow, meaning there will be a lot of number of nuclei, but size will be very small. So there will be a lot of so this nuclei after growing, the two nuclei are keep on growing, right?
Yes,
So
yes, ma'am.
here this laser point is, yeah, visible, right? So
Yes,
this one nuclei and this one nuclei, these two are growing, and at this particular place, these will these are growing and these will stop, right? So they can't grow in another nuclei, right? So this, after this, there will be this barrier, this particular point, this grain boundary, it won't be having this type of crystal structure. So
so,
these will be forming during your casting of material.
so that means, ma'am, it is due to means the temperature is the one of the parameter to
Yeah, cooling rate
formation.
is one of the parameters. So how fast you are cooling your material, how much, because if you are cooling very slow, then a lot of time will be there, so growth will be will be higher, so less number of nuclei will be there. So it
Okay.
depends on cooling rate basically.
Uh, Ma'am, in the first unit, I think so. Sir told that to one turbine blade are made up of a single crystal.
Yeah,
That means there is no grain boundaries there.
yeah, there is no
So
grain boundary. So there is a material will be eh, this structure you can see, right? So
yes,
there
ma'am.
can be dislocations can be there, some other imperfections such as vacancy can be there, but this type of grain boundary won't be there. These grain boundaries won't be there, there will be only single crystals. So those single crystals are formed with other processing units, processing methods. Okay, so that is not like normal cooling type of processing is not used for that.
Okay, ma'am. So due to that, the some specific property are means increases on that materials.
Yeah, so in that case, your material, if you don't have these grain boundaries, what happens? These grain boundaries provide diffusion easily. So if your material has a lot of grain boundary, this diffusion will be very easy at higher temperatures and your material will be weak at higher temperature. So in case of turbine blades, they are used at high temperature and you require very less creep. So for good creep properties, you use single crystal type of structures.
Okay, ma'am.
Okay.
That means the manufacturing process is different for the others. This
Single crystal type of structure, yeah. For polycrystalline materials, like from other methods also, such as other than casting also, such as electrodeposition, this phase vapor deposition, also you get polycrystalline type of structures. So the method for single crystalline is different compared to these methods, these polycrystalline materials.
clear, ma'am.
Okay. Next is solid solution strengthening. So in this case, pure metals are almost always softer than their alloys. So also you can see, if you take gold, which is 100% pure, then it will be a lot very soft. You can't even make it into jewelries. So for that you add some impurities to it. Only then you can make it into jewelries or other uh, structural some elements to it. And by adding another element which goes into interstitial or substitutional positions is a in the solution, it increases strength. So no, I haven't added that particular slide, but it will be like this. So these blue atoms here, you can see these will be of different element. So if they are there, then there will be some strain field to your material, which will be providing some strain to your material. And if these are the substitutional type, and if it's sitting here at the pointer that I'm showing, if it's sitting in between, then it will be interstitial type of structure. Okay, so adding another element which goes into either interstitial or substitutional position, it will be increasing strength. The impurity atoms, they cause lattice strain which can anchor dislocation. So it will interact with the dislocation. That's why alloys are stronger compared to pure metals. So here also you can see, as you keep on increasing the nickel content in copper, your strength will keep on increasing. And as I told earlier as well, tensile strength and ductility has almost always inversely proportional relation. So ductility for material will keep on decreasing as you keep on increasing nickel content. Next is strain hardening. So in this case, you have enhancement of strength with increased plastic deformation. So if you are plastically deforming your material, you will be you will be having a lot of number of dislocations which will interact with each other. Okay, so strain hardening is a phenomena whereby a ductile metal becomes harder and stronger as it is plastically deformed. And it is also called work hardening or cold working. because of the temperature at which deformation takes place is lower compared to melting temperature, and the effects of strain hardening may be removed by annealing heat treatment. So if you have deformed your material and you are heating this material at temperature higher than recrystallization temperature, then your material will regain its initial ductility. This heat treatment, annealing heat treatment, meaning slow heating and slow cooling, and in this case your strength increases but ductility is sacrificed. So here, as you keep on, you can see, as you keep on increasing the dislocation density, your strength of material will keep on increasing. These both have proportional relationship. Next is precipitation or edge hardening. So in this technique, it is used to increase the yield strength of malleable materials like aluminum, copper alloys, stainless steels, etc., and based on changes in solid solubility with temperature to produce fine particles of an impurity phase which blocks the movement of dislocations in a crystal's lattice. So this is the initial structure, supersaturated type of structure. Here after this, if you keep on heating your material, these particular solute atoms, they will come together and form a this precipitate phase. Then this particular phase will have some interface energy to it. So if there is a dislocation will be moving in this particular structure, then it will provide hindrance to those dislocations and it will be providing precipitation hardening. The alloys must be kept at elevated temperatures for hours to allow precipitation to take place, and this time delay is also called aging. So here also you can see your firstly heating your material to single phase region and you're quenching your material. So after quenching, your material has a single phase but it is in supersaturated state at a room temperature. Then because of this supersaturated stage, it is metastable. So if you will be heating it to very lower temperatures, then there will be formation of precipitates and known as precipitation heat treatment, and the first one was called solution heat treatment. Okay, and after that you will be getting precipitates. Next is corrosion of metals, Pilling-Bedworth ratio. This is for good oxidation resistance. The oxide should be adherent to the surface, and if this Pilling-Bedworth ratio is less than 1, then the tensile stresses in oxide film will be brittle oxide which will be cracking, and thus it will be unprotective layer. Okay, so if this ratio is less than 1, meaning here you can see the ratio, it's volume of the oxide formed divided by volume of metal consumed in the oxidation. If the volume is less of the oxide form, if volume is less, then there will be this type of tensile stresses there. So this breakage will be there. Okay, and if this buildup is also higher, if this is higher than 2, then there will be compressive stresses. So this volume will be higher for this oxide, then this type of peeling would be there. So the oxide cracks and flakes off, and this will be again unprotective type of layer. And if this is actually in between 1 to 2, then there will be compressive stresses in oxide film which are uniformly over a metal surface, and it will be making a uniform layer coating on this particular metal. This oxide layer will be there and there won't be any further oxidation. So for metals, for which metals this Pilling-Bedworth ratio between 1 and 2, they will be providing good corrosion resistance. So for these particular elements, you can remember that which one are in between 1 to 2, so that if you are asked question, you can reply. So between K2O, Na2O and magnesium oxide, these are all unprotective. So these ratio are below 1. and alumina, nickel oxide, copper oxide, and chromium oxide. These, I also told that these are also added in steel for increasing oxidation resistance. And also these metals, when they are used in pure forms, they provide good corrosion resistance. So these metals are good oxidation resistance because of this reason, because their oxidation layer which is forming, it is uniform and it doesn't flake off. And in case of iron, you know that your iron and steel is easily corroded, so that's because its PV ratio is 2.16. Next is ceramics. So
Ma'am,
yeah,
ma'am, the previous slide, could you show me again?
this
Ma'am,
one or before this?
yes, ma'am, this one.
Yeah,
So here, ma'am, the PB1 is greater than 1. Okay, so aluminum oxide is also act as a, ma'am, abrasive material.
aluminum oxide as abrasive material. Yeah, aluminum oxide is also used in polishing materials as well. So as a abrasive, so you can use it for that as well. So in that case, you are using alumina particles separately.
I'm not understand, ma'am, because my question is that still aluminum is a metal, but when it is in the in but aluminum oxide is a not a metal, but it is used for the abrasive particle. So how it is possible, ma'am?
So aluminum is, when it's reacting with oxygen, alumina meaning it's ceramic, right?
Okay,
Cl2O3 is ceramic. So ceramic can be used as abrasive. Abrasive when you use when it has higher hardness. These particles are ceramic, so they have high hardness. So when you are using these metals as abrasives, what you are using? You are using your metals against these ceramic particles. So these ceramic particles will form scratches and it will keep on polishing your material to higher surface finish. When you are using aluminum, so aluminum, on the top layer of this aluminum, what will it do? It will react with oxygen in environment. Okay, so there will be very thin layer formed, so it will be in very micrometer size. It won't, this size of this layer won't be very high, but it will be in micrometers only. So there will be alumina layer formed on the aluminum, or on nickel as well, on copper as well. There is always these layers formed on the metals. If you
clear,
can
ma'am.
be having these pure, if the pure metals will be there, then alumina is very reactive in nature.
Clear,
That's
ma'am.
why yeah. Okay.
Yes, ma'am. Yes.
Next is ceramics. So ceramics word is derived from the Greek term keramikos, meaning burnt stuff. So clay is the earliest known ceramic which is used for making pottery, and the ceramics materials are inorganic crystalline materials which are made from compounds of a metal and non-metal, primarily held by ionic and covalent bonds. The glass by definition is not a ceramic because it is an amorphous solid which is non-crystalline, but its mechanical properties behave similarly to the ceramic materials. The common characteristics are hard and brittle. So ceramics are always hard and brittle. Carbon is in the form of a diamond which is hardest known material, strong in compression. So if you are compressing your ceramic, it will show good strength. So typically 100 times the when it's in tension, while they are weak in tension. Chemically inert, ceramics are inert in chemically. So against, you can store some chemicals, harsh chemicals in ceramics easily, and insulators of heat and electricity because there are no free electrons. Except carbon in the form of diamond and graphite. Diamond is an graphite is both thermal and electrical conductivity, but diamond has this heat conductivity, not electrical conductivity. Next is high and well defined melting point. The classification of ceramics. So there are natural ceramics, which is limestone, calcium carbonate, Abrasives which are used in for abrasion, so silicon carbide, tungsten carbide, alumina or corundum, and silica sand. Refractories: alumina, silica, bricks, fire clay, zirconia, magnesia, barium oxide, etc. Glasses: non-crystalline silicates containing other oxides such as calcium oxide, sodium oxide, potassium oxide and aluminum oxide, etc. Piezoelectric ceramics containing barium titanate, lead titanate, lead zirconate titanate known as PZT, and potassium niobate. Next is bonding in ceramics. Okay, so in case of bonding in ceramic, it can be of two types, ionic and covalent. So many ceramics exhibit a combination of ionic and covalent bonding types, the degree of the ionic character being dependent on the electronegativity difference of the atoms that are forming ceramic. Okay, in case of ionic ceramics, ionic bonding is predominant. They are compounds of a metal and a non-metal. Okay, and the electrostatic attraction between the unlike charges is responsible for dense packing. Examples include NaCl, MgO, zirconium oxide and alumina, etc. Next is covalent ceramics. So in these examples you can see the sodium and chlorine sit very far in periodic table, similar to aluminum oxygen, zirconium oxygen and magnesium oxygen. Next is covalent ceramics. In this case, covalent bonding is predominant. These are the compounds of two non-metals or occasionally pure element such as diamond, carbon. Next is bonds are formed by sharing electrons with their neighbors to give a fixed number of directional bonds. Examples include silica, graphite, diamonds, etc. Next is failures in ceramics. So ceramics have negligible plastic deformation before fracture and they give no warning. So they are very brittle in nature, that's why they show catastrophic failure. Next is the brittle fracture of ceramics limits their applications. Failure in ceramics occurs due to the unavoidable presence of microscopic flaws such as micro cracks, internal pores and atmospheric contaminants which result during fabrication. Okay, so all ceramics, they are more likely to consist some pores already in it, pores or some micro cracks which lead to their failure. The inherent flaws, they lead to crack formation and propagation. Ceramics are good structural materials under compression as difficult for cracks to propagate. So if you are compressing your material, your crack is not likely to propagate. The flows cannot be closely controlled in manufacturing, which leads to large variability or scatter in the fracture strength of ceramic materials. Okay, any query till now? I'll repeat the questions once again.
No, ma'am, clear all.
Okay, so I'll just repeat the questions once again. Okay, so first question was which form is degradation form in polymers? Your options were swelling, dissolution, corrosion and damping.
Swelling.
Okay, swelling because of swelling will be when your solvent can penetrate. Swelling is the penetration of a solvent into polymer network which can cause an abrupt change in the volume, and corrosion will be in case of metals. Next question is iron carbon alloy containing less than 0.83% carbon is called. The options are high speed steel, hypereutectoid steel and cast iron. So correct answer
Hypoeutectoid.
hypoeutectoid steel. So for answering these type of steels you should remember this particular diagram. So here You have to remember at 0.8% you have eutectoid steel, and for 4.3% you have eutectic type of composition for cast iron. So below that you will be having hypo, above that you will be having hyper, and also in case of eutectoid and eutectic both.
Yeah, it is quite little look like a tongue twister hypo height.
Yeah, hyper will be higher, so you can keep like that, er meaning higher. Okay,
Yeah,
so
yes,
you
ma'am.
can
Yes,
like,
I got it.
you can find some trick to remember it. So hyper meaning higher or something like that.
And the another thing, ma'am, and the same thing, the which material possesses which property or the ingredient, if we add it, which type of strength is increased. They are quite similar, little different. That is a little tricky thing to remember.
Yeah, so you should remember like what is difference to them. For example, you remember cobalt for high temperature or something like that. You need to make notes so that you can remember those. Vanadium for like grain refinement, so that those particular you can remember, and other will be similar. So all these will be increasing strength, but what is distinct part? So distinct part you need to remember, like sulfur is always increasing brittleness, sulfur and phosphorus are increasing brittleness, and then manganese is providing hardenability, manganese and boron. So you can like club those as well, like which things are providing hardenability, which thing is providing hot heat resistance, which thing is providing corrosion resistance. For corrosion resistance, basically, which are providing filling bedworth ratio between 1 to 2. So nickel, chromium, copper, these three will be the ones which will be providing good corrosion resistance. So
Yes,
that's
ma'am.
how you need to, if you will be reading it multiple times from your notes, then you will be remembering it easily. Otherwise, if you read it after many days, you won't be remembering.
Yes,
Okay.
ma'am.
Next is, which of the following example is mechanical metamaterial? So this one will be origami type of structure, which are some 3D structures. Okay, and then you have ledeburite microstructure in eutectic steel, which consists of alternating layers of two phases, austenite and cementite. Okay.
Cementite.
Hmm. And ledeburite is similar to your cementite, in not cementite but pearlite. In case of pearlite, you will be having alternating layers of ferrite and cementite. So this is similar to that. So ledeburite will be only, difference will be austenite. Next is which type of mechanical metamaterial? Then again you have origami type of metamaterials. And in this case, which of the following is example of mechanical metamaterial with a negative Poisson's ratio? So this one will be auxetic
First.
form. Okay, so these are pretty straightforward. Then again something related to steel. Now this one is the type of questions you will be able to answer if you remember those, you make those type of notes and you remember those. So for nickel, all things will be basically increasing hardness, so this one you can't like differentiate, but nickel will be basically used for increasing
The
your
strength.
corrosion resistance and improving. But it, one of the major thing that we studied today, that nickel, it will be improving strength without
Ductility.
deteriorating ductility and toughness.
Yes, ma'am.
So that will be a star point for nickel, so that you should remember. And then cobalt, cobalt is always for high temperature, so you should remember that particular part. Sulfur and phosphorus both decrease brittleness, both increase brittleness. And chromium always improves oxidation and corrosion resistance. Next is carbon steel. So steels will be having less than 0.21% of carbon. Okay, and in case of cast irons, you'll be having more than 2.1%. 6.7 is percentage for the cementite. So in cementite, what is the percentage of carbon? Then this will be the correct answer. Then,
Ma'am,
yeah.
ma'am, actually in the furnace, how they add carbon, or in which form they add the carbon in the steels? Means, what is the carbon form they add in the steels in the furnace?
Okay, so
Is it
okay, I told earlier as well, like it can be added in pig iron form. So it depends on which process you are using for steel making. So if you are using recycling, then you are adding steel scrap. So steel scrap already have carbon percentage in it. And also if you are using pig iron, then it has carbon percent is as high as 4 weight percent. So you need to reduce the carbon percentage, not add carbon. So for that you add oxygen to it. So oxygen will be taking care of carbon and it will be forming CO2.
Okay, okay,
So
clear,
it
ma'am.
depends on whatever process you are using.
Okay, ma'am. That means already
Carbon will
already
be
existed there.
already present, and you
We
also
need to
add
remove
coke.
it.
Yeah, coke is also added in the iron ore. Then also from that also your carbon can come into that, depending on whatever process that you are using.
Okay, ma'am.
Which cast iron has graphite in flake form? So white cast iron, it will be in cementite form. Gray cast iron, it will be in flake form. And in malleable cast iron, it will be irregular shape. In nodular, it will be spherical type of structure. Next is, here you have to simply use the Hall page
Hold
relation,
on.
sigma y equal to sigma naught plus ky divided by under root d. So you are given all the things for one of the situations. So ky you have to find out. Then you just put ky value for the 100 nanometer. Then you will be getting the yield strength for that particular uh, grain size.
And this relation is not applicable below 10 nanometer.
10 nanometer, yeah. Next is, what is the type of steel with 1.1 weight percent carbon? So it will be higher than 0.8, meaning hyper eutectoid. And which one of the result of increasing carbon in steel? So carbon will be increasing hardenability. Ductility will be reducing, machinability will be reducing, as well as weldability will be reducing. And weldability and hardenability are always inversely proportional. So that way also you can remember. Okay, if you are increasing your
Yes,
materials
ma'am.
hardenability, then your materials weldability will decrease, because if it's easily forming martensite, then your weldability will deteriorate. Which metal is used as sacrificial anode? Your options are gold, silver, zinc and copper. So zinc is the one which is highly reactive, so it is used as sacrificial anode. Which of the strengthening mechanism is the result of dislocation multiplication? Strain hardening, composite strengthening, grain refining, solid solution strengthening. So strain hardening will be the one, or work hardening, cold working. These are the some of the other names for this particular strengthening mechanism. But dislocation multiplication is the reason for strengthening. Next question is, which metal oxide provides good adhesion to metal following pilling Bedworth ratio, preventing corrosion? So options are magnesium oxide, iron oxide, sodium oxide and nickel oxide. So nickel is the one, nickel, chromium, copper. These are some of the elements which provide good adhesion. So these other won't be correct answers. These were the classifications of metals. Check if these were the classifications of metals, ferrous and non-ferrous. Then classification of steel, types of steels, and you should remember some of the applications as well. Then tool steel, stainless steel. Then these are the effects of some of the alloying elements. So a lot of questions will be asked based on this, so you can remember this. You should try to remember this particular table, like what are the roles of various impurities and some of the alloying elements for the steel. Okay, I think that's it from my side. Okay.
Yes, ma'am.
Okay.
Ma'am,
Yeah.
Ma'am, I have some question not regarding this course. So can I ask during the recording or after the recording?